Ladies and gentlemen, I welcome you to the session 2, afternoon session, titled as Advanced Manufacturing. And it's probably time to start with the first talk, which will be given, to my knowledge, it is invited talk to be given by Professor Darius Gailevicius. And the title of the presentation is here as Optical Drill, Twisted Beams. So, Andrei, you are probably supposed to present a short biography of the presenter, right?
Thank you. Yes, I can present the biography. So, Professor Darius Gailevicius finished his PhD in 2019 at Vilnius University. He is focused on micro and nanophotonics research in relation to structured light applications in compact laser systems and various approaches to femtosecond direct laser writing facilitating approaches.
Okay, so thank you very much for the introduction. At the moment, I'm not a professor yet, but thank you for fast forwarding me to that nice position. So allow me to share my slides. Can you confirm that you can see them?
Yes.
Okay, thank you. So to begin with, my talk is titled Optical Drills and Twisting Beams. And it's an ambitious talk, of course. We didn't finish applicating those structures, but I will tell you a story on our current pathway to the application. So to begin with, everybody knows about optical trapping. Of course, you can trap particles in using a focused laser beam, using either momentum transfer or even thermal gradient effects. By scanning the beam, you can basically move the particles around and therefore facilitate mechanical impact by using optical means. So the question is, can we use it for something else, not only just moving particles around, but basically building a drill bit out of it? Of course, the function of the drill bit is not only processing the surface, but also taking out the material out of the hole. Where would it be useful? So the first example comes to mind is femtosecond surface processing. And it's characterized by the fact that when you're ablating a surface using ultra-short pulsed beams, at time scales larger than the pulse duration, debris plumes are generated, which produce scattering, reflecting, and otherwise not useful scatterers in the optical path, which you have to remove somehow or wait to dissipate until delivering the second pulse. Therefore, the only way to increase processing throughput is usually either tuning some parameters which allow to depositing more energy into the surface of the treated sample, or increasing the pulse energy trivially. But you cannot increase the pulse repetition rate because the subsequent pulses will encounter the said plume. So an optical drill, its function would be not only to drill, but also to impart force on the plume to facilitate a different approach to the removal of the material. So the basis for the optical drill is a type of structured light or beam, which is called helical beam, twisted beam, topological beam. There are many names, but the idea is that using special beam shaping approaches, you can produce two, I will emphasize this, intensity, not phase, intensity, rotating patterns. Rotating means changing over propagation length, to either image objects using special point square functions, or basically trap them inside a spiral pathway and use the fact that such beams usually feature angular momentum, which causes the particle to basically move along the spiral track. But this is too easy. we don't want the particle to move along the spiral trap on its own. We want the trap to be to be dynamically moving together with the particle to facilitate faster actuation, or let's say mechanical impact. Okay, so some terminology. The beams which contain a helical phase are usually called spiral vortex or vortex beams. And in the intensity domain, they are characterized by a tube-shaped intensity pattern or a donut-shaped intensity pattern. There exist other kinds of beams, helical beams, which I mentioned previously. They have an intensity pattern which resembles a spiral structure, can contain one spiral structure, two spiral structures or windings, three spiral structures, and so on. And if you know how, you can impart dynamic movement on the structure for it to be changing in time. So how to do it? This is what we are trying to examine. The idea is to use Bessel beams, mix those Bessel beams, and also impart rotation and with some analogs from acoustics. Okay. In wave physics, doesn't matter optics or acoustics or whatever, the method to generate such beams is to take a Bessel beam, for example. Here is the equation describing the complex amplitude of such a beam in polar coordinates, and it's characterized by the parameter m, the topological charge, and the transverse and longitudinal wave vector components, which are associated with the wavelength or frequency of the wave. So if you have one vortex beam, well, you have only the phase change. If you have another vortex beam with a different topological charge, you still have a phase change. But if the beams are combined in one single optical path, you can produce that legendary spiral beam, which spirality or the period of windings in space you can control by tuning the phase front windings, D1, D2 of the initial beams. So in the cross-section domain, the intensity looks as shown on the bottom right. Basically contains along the Z rotating intensity maxima. It can be 1, 2, or more. And it resembles a drill bit quite well. Okay, so how can one implement this? Well, in acoustics, it's a quite straightforward approach. You can have phased array transducers, which you can run at different frequencies. It's easy to do electronically. You can arrange them as you want. You can even shape them by your hands. And if you have a composite transducer, as shown on the bottom here, which has a section 1 generating a first spiral beam, vortex beam, sorry, and the second transducer generating a second spiral beam, you just need to turn them on simultaneously with different frequencies, and then you can produce that dynamic structure. In terms of intensity distributions, it looks like this. Here we have the transverse cuts of the patterns in XY plane, and on the right-hand side, we have the longitudinal cuts. So at the top, topological charge of 1, in the middle, a topological charge of 2, and at the bottom, the combined result having a difference in topological charge 1 and a frequency or wavelength offset to facilitate movement. In acoustics, it looks like this. And well, as mentioned previously, the number of windings can be controlled by tuning the topological shift. For example, 4 and 5 topological charges produce 1 winding. 4 and 6 have a difference to produce 2 windings, and 4 and 9 have for 5. So 5 windings. Okay, so how does it look experimentally? Here we have a meta-surface acoustical transducer based on 2 spiral gratings and 2 sectors. Allow me to play it. Yes, this is an experiment. I hope you can see it. Here on the surface of water, we have 3 lobes, 3 pressure waves that are rotating in one direction and faster, then slower, and then it's reversed, basically in the frequency domain, to rotate it in the opposite direction. So mechanically, acoustically, it works. Okay, what about optical systems? Well, in optical systems, we do not have phased emitters. It's not easy to facilitate such devices. So the simplest approach is to use hexagon lenses or conical lenses to produce said Bessel beams, as shown on the top. There are other elements which are called spiral phase plates. They can impart that phase or topological charge onto a beam to produce a vortex beam, which has the cross-sectional evolution of intensity as shown on the right. And the combination of those elements can produce a topological Bessel beam. So this is what we want. So if we think about a double sector hexagon phase element, as shown here on the right-hand side, we can produce from a single beam, laser beam, which is coherent unto itself, 2 overlapping Bessel beams, and basically engineer the situation that I showed previously. So to give you an idea how does it look like, and I am showing these numerical simulations for 4 spiral arms and 3 spiral arms, evolving at a millimeter scale up to 300 millimeters or so, showing the cross sections of the structure, how it rotates in plane, if dynamically actuated, and how it proceeds along the z direction. What about the implementation of such devices? They are difficult to make. It's much easier to use a spatial light modulator, which allows us to project any element that we like with some limitations. In terms of resolution, we can produce phase hexagons or phase spiral plates, which are combined to produce a hologram as shown on the bottom left. We just need to illuminate the spatial light modulator and project the beam onto some detector, for example, a CCD camera. And we can observe these patterns which we predicted. So this is an experimental image, no longer numerical. It shows how for a visible wavelength laser, we managed to produce around 200 millimeter long area at which the spiral structure develops. Everything, again, is in spiral domain. This is not a holographic technique. It's direct linear observation of the structure. And to impart rotation on it, well, we cheated a bit. It's not easy to coherently change the wavelength of beam number 1 and number 2, but we can basically impart rotation on one of the holograms, for example, the central structure, to simulate the effect of mismatched wave numbers. Here you can see a simulation on top. Here, the simulated effect on the right, it's the dynamically rotating beam pattern as observed experimentally. So the limitations of this kind of approach are as follows. If you want to go to higher topological charges, might of course be a benefit, such as 1 and 4, 2 and 5, 3 and 6, 4 and 7, 5 and 8, 6 and 9, and so on. The beam diameter, or the diameter of the tube, is increasing up to a millimeter scale structure, in our case at least, for the resolutions that were available for us. The smallest beam that we produced was of a diameter of around 150 micrometers. So it means that for very high arm numbers, you have to take precautions in managing this pattern. And for not only observations based on CCD plane, CCD camera-based plane observations, we made another test. Well, we wanted to see the structure directly and without intermediate tricks. So we formed such a beam and illuminated a fluorescent dye. And we observed the structures sideways as they produce the windings along its propagation direction. So at the bottom here, we have 3 moments in time, T1, T2, T3, showing different 2 winding beam evolving as we are watching it. To be particular, here are 2 examples of clockwise rotation and counterclockwise rotation. This is a movie directly from the experiment, or SLM device could function at a frequency repetition rate up to 60 Hertz. So it's not rotating very fast, could be faster, but it's visible by human eye. And even clockwise rotation is very easily facilitated. So I hope that this convinces you that we can generate these exotic spiral beams, dynamic helical beams, and that the progression to future experiments concerning the manipulation of matter will be successful. So what we foresee in the future is use of coherent approaches. Here we used spatial manipulation of the holograms, but we would like to detune one good quality spatial temporal beam into 2 parts and basically produce gigahertz and higher frequency rotating beams. Linear velocity will be very, very high. So we can even excite, hopefully, some electronic effects on conductive surfaces, and also demonstrate that particle extraction that I talked about, just as we will proceed to higher powers and better resolutions. So for further questions, I'm always available, and I thank the student Gabrielis for making the experiments, for colleague Noah from Valencia Polytechnic Institute for the acoustic experiments, and Kęstutis Staliūnas for the idea. So thank you very much for listening. And
thank you very much, Dr. Gailevicius, for an extremely attractive presentation and talk. So the paper or presentation is now open for discussion. I already see raised hands. Professor Malinauskas, please.
Yes, thank you. Dario, I would like to ask from your shown results, it seemed like the aspect ratio of this drill is very high, right? It's very long and very narrow. Is it possible to manipulate so that it would to the real mechanical drill we imagine? Or if not, what are the reasons, and could it be potentially overcome in, I don't know, with some other solutions?
Yeah, thank you very much for the question. So the drill was very large aspect ratio because, well, the SLM device that we used had, I don't remember, 14 micrometers pixel sizes or something like that. So it's difficult to project a very high cone angle axicon and combine it with good resolution with the spiral base plate holograms. Therefore, we had to make compromises and to produce longer drills, which of course were easier to observe with the CCD camera. It can be downscaled properly using passive elements without prototyping, of course. So it can always be smaller. At the large scale, of course, in the radio technology, it could be probably kilometer scale or meter scale. Yes, so thank you very much for the question.
But to get it correctly or fully, so if you had a higher spatial resolution SLM of more pixels or smaller pixels, or preferably both, you could change the aspect ratio, yes?
Yes, that's correct.
Okay, so its technical limitation is in the active phase mask SLM in this case, yes?
Yes, one of the largest problems in combining the apertures of the elements further on in SLM, yes.
Okay, good. Thank you.
Thank you.
Thank you. Professor Anand, please.
Okay, yeah, thank you, Darius, for the very nice presentation. So I think your method can replace the mechanical drills for advanced manufacturing. Yeah, so I have a question related to the field. So you have shown the intensity and phase variations, which is quite interesting. But can you comment on the Poynting vector distribution? Because in the final slide, you also mentioned that it has a possibility for, say, 3D optical trapping. So when we do this 3D optical trapping, we pre-calculate this Poynting vector distribution to understand how the force field act. So yeah.
Okay, so I cannot offer a proper comment on that. At this point, since we were using a scalar model for the intensity distribution, we do not examine it. However, people who only use this for optical trapping and moment transfer, I will point out the relevant reference here. Please, 1 second. Yes, at the bottom right here, I have calculated the vector field, which basically impacts the angular momentum on the particle passively. So we demonstrated that the passive structure with switching topological charge can cause the particle to move up or down. So I guess this is the best reference I can offer, the most concise answer.
Okay, yeah, thank you very much. But I think it is also possible to calculate this Poynting vector for scalar fields, because you have this phase information. So from that, I think it will be quite interesting to see, because you have this spatial as well as temporal variation of optical field. So I think we can see how the arrows vary with respect to time and space.
Oh, that would be very interesting, actually.
Yes.
So please don't forget my contacts.
Yeah. Thank you very much. Yes.
Thank you.
Thank you. More hands? Questions, comments? Do not see here. I can ask, as from a point of view of process engineer, material scientist, not really a specialist in the field. You mentioned this 3-dimensional particle trapping a couple of times. What kind of particles we exactly are talking here about?
Okay, so the particles depend on the nature of the material. If it's, let's say, a metal surface, then of course they are absorbent metal particles, maybe metal oxide if processed in an oxide environment. So their sizes can vary from nanometers to micrometers, a few micrometers. If the material is transparent, such as glass, you can produce silicon dioxide particles, which are liquefied. So in one case, as I mentioned about the thermal effects, the idea is to produce strong thermal gradients migrating on the surface, not exactly to extract, but to basically direct the direction at which the fume is ejected. And for the dielectric particles, the attraction part is the more interesting, because the material is not absorbent directly, yes? Unless it's in plasma state, yes.
I see. Thank you, really. So it's the material's properties, what such kind of drill can influence or affect are those, so it's optical yes. Response, basically. Yes. And this trapping also means that, but it can't be really a physical trapping, right?
Yes, it's not exactly...
Not a mechanical.
Yeah, it's not mechanical. Well, the thermal field, it's in a hypothesis state, yes.
I see. Well, thank you very much. So no more questions? I do not see. Well, then let us thank the speaker, Professor Gailevicius again.